Good morning, students. We continue with our discussion of velocity time graphs today. And today we are going to discuss few situations as special cases in which velocity time graph is given in the questions, and we have to interpret the motion of that object, and in some cases we have to do some calculation to find out the acceleration involved, the distance involved that the object has covered. So velocity time graphs are important from the examination point of view. These are the situations which are particularly important. Number one, velocity time graph of an object that is allowed to fall from a small height. VT graph, which is already here written at the top, for an object dropped from a small height. Dropped from a small height. Because the object is dropped, so initial velocity is 0, so the object must start from the origin. So V and T written on these two axes, and this is expected to be a straight line because the acceleration is constant. So this is acceleration due to gravity, which is constant. So approximately 10 meter per second square should be the gradient when you calculate the acceleration with the help of a graph like this. This line continues as long as the object falls, but obviously this is not going to be a very large time for which the object falls, because it's few meters through which it falls. Number two, if the object is dropped from a large height, a tall building, a high cliff, words like this will indicate that air resistance cannot be ignored now. Air resistance is now appreciable. So instead of a straight line, it will start developing into a curve, and then it becomes a straight line. During this time, the acceleration is decreasing. So this is acceleration decreasing. And ultimately it becomes A equal to 0, which means acceleration has become 0 now. The object has started moving with a constant velocity, and that is known as terminal velocity or terminal speed, because the object is moving along the straight line. They might call it terminal velocity or terminal speed because it does not distinguish between the two. So terminal velocity, a useful concept. We'll discuss it later in chapter 5 as well. Why terminal velocities are achieved, what forces balance, and then what calculations are possible. That will be discussed in more detail in chapter 5. So this is always the shape of the velocity time graph for an object which is dropped from a large height, from the top of a tall building, or from a high cliff. Any word like this will indicate that air drag is appreciable. So in the presence of air drag, acceleration cannot remain constant, although initially air drag is not that appreciable, because I told you it increases with the speed. So as the object gains more speed, as it accelerates, at a certain value of that speed, acquired, the air drag starts becoming more significant. It opposes its fall. So acceleration starts decreasing, although speed still increases, but at not that rate at which it was increasing initially. So the acceleration decreases, and ultimately it is the maximum speed with which it falls. It cannot increase any further. So these are two important situations. Then for another situation, for an object dropped from a small height, and it makes an impact with the ground, and rebounds. So those situations in which an object is dropped through a small height, it makes an impact with the ground, it rebounds, then makes another impact, then rebounds. What is the shape of that graph? That is also useful because we have questions related to this case. Because it is dropped from a small height, so initially it is expected to have the same shape as discussed earlier. So straight line. It falls through a small height, and this is the velocity it has gained on reaching the ground, and then it makes the first impact. This is first impact. But what happens when an object makes an impact with the ground? There are at least two things that happen immediately. The object for a moment comes to rest, and then it changes its velocity, its direction in the upward direction, and these two are depicted like this. Let's say it doesn't take practically no time to make an impact and change velocity. It immediately happens. So you can make it almost a straight line, and it's not necessary that it rises with the same speed with which it made the impact. So this might be, let's say, 10 meter per second square, maybe. This might be slightly smaller magnitude. This may be -9 meter per second or even less. So it rises, and this is a parallel line to this. But this is actually the speed with which it rises after the impact, slightly less than this. This is positive because it was downward. This is negative because it is opposite in direction now. So they have to be opposite signs. Why is this line and this line parallel? Because this and this represent the same acceleration. So 9.81 will be the acceleration, again the gradient of that line, which shows the change in velocity. So with negative values, when we calculate, it will come out to be 9.81 again. And this is where the object rises to its maximum height. So it comes to rest. After this, the object starts falling again, and this line continues in the same direction. Now, the size of this triangle should be same as this triangle. let's say another rebound and still less velocity now, then parallel line, then it continues, and then same size of these two triangles. These two are same and these two are same. Why these two triangles should have same size? Because the area of this triangle is the height through which it rises, and therefore it should be the same distance through it falls, because this is the maximum height to which it has risen, and after this it falls, and this is the second impact that it makes, this is the third impact that it makes, and this continues. So triangles will go on becoming smaller in size as expected until the object comes to rest. So what you need to understand is where the impact is made and what should be the relative sizes of these triangles, what they represent, how we can calculate the acceleration of the object during this fall. So all these are important points. I quickly repeat, this line represents the acceleration, which remains 9.81, whether the object goes upward or it goes downward, it is always 9.81. I mean, the magnitude is always 9.81. Because this is always like this, so the value is expected to be positive. 9.81 will be positive because the gradient is positive of all these lines. The area under this should be same because the two represents the same height through which it rises and then through which it falls should be same. Similarly, after the second impact, the object rises through a certain height, and that is equal to the area of this triangle. So this triangle should also have the same area because the object will fall through the same distance. So the third point is, the last point, why the sizes of these triangles should go on becoming smaller, because the kinetic energy is lost in each impact. Some energy is lost in each impact. So the object rises to a smaller height because it rises with a smaller speed on impact. So that is understandable. Let's move on to another situation. An object is which is oscillating on an end of a spring. We have a question on this situation as well. When you have a spring like this and you attach a mass to this, let's say this is its equilibrium position. When you leave it in its equilibrium position, it stays here. Then you pull it down, let's say to this position, and then you allow it to oscillate. It moves up and down between these two extremes. This is one extreme to which it goes, and this is the other extreme to which it goes when it moves to this direction, downwards. So it moves down, then it moves up. So this up and down motion is represented with the help of a velocity time graph. How is velocity changes when an object oscillates in this manner? It is attached to a spring. Obviously, the object, when it goes to the top, it comes to rest for a moment there. Then it starts moving down with a large speed. It passes from the center. Then it goes to the other extreme, slowing down. and then comes to rest when it reaches this point. So rests are those positions which are shown as two extreme points. We can label these points as A and B. So A and B are those positions where the speed should be 0. However, when the object passes through the center while moving down or up, it is moving with a maximum speed there. So this situation is represented in this manner. This is the kind of graph you will see, and with some description added, they will tell us that object is initially pulled down to a position B, let's say. So this is initially the position B. This is B. And when you allow it to move to the top towards A, it passes through C. So this position must be C, because the object is moving with a maximum speed there. This is the maximum speed which we can read from this axis. But it continues to A, and then it reaches the position A, and there it comes to rest for a moment. But then it starts moving down, and again it passes through C, and there its speed is maximum again with the opposite direction, and therefore its sign is negative. These two are same velocities with opposite directions, so opposite signs, and then as it moves towards B, further down, it comes to rest. So it started from B and it has come back to B, making a complete round trip. During this complete round trip, the object has passed through C twice, through the center twice. There the acceleration is 0. But at other positions like this, the acceleration is maximum. So at extreme positions where the object comes to rest for a moment, acceleration has the largest value there, and in between these two, the acceleration is decreasing. So it is the same sad phase that I discussed earlier. If you have a curve like this, the acceleration decreases. For another object, velocity time graph for an object thrown vertically upwards. Vertically upwards. When we throw an object vertically upwards, the initial is time. This gives you the time when the object has position at maximum height. So it might be, let's say 3 seconds later after you have thrown up. You can calculate with the help of this velocity how much time it takes to reach the maximum height. You can use an equation of motion quickly to work out what time it should be. If I know the final velocity is 0 at the maximum height, that means this can be quickly worked out using this equation. V 0.5 here, then 1 second here, 1.5, and then 2 seconds later, this will be at the maximum height. But what happens after it reaches the maximum height? It doesn't stay there, obviously. It starts falling down. This graph now shows the velocities in the opposite direction. So if during the upward motion, all the velocities are taken positive, now that the object has started falling down, it has changed its direction, so all the velocities will now have negative values. So this object, this graph continues in this manner. So straight line. It's the ground. If it is thrown at, let's say, if the object is thrown at this height and it comes back to the same level, this is the kind of graph we expect. But what if the situation is slightly different? Although it is thrown from here, but it doesn't land here, it lands at a surface above this level. It lands on a building nearby. You have thrown an object like this, but while coming back, it falls on the roof of a building nearby. So it is a situation like this. For this kind of situation, this will end here. Obviously, it has not fallen that much. So this is a much shorter triangle, therefore a much shorter distance through which it falls. Although it has risen through a large height, because it has started from this point, it has gone all the way to this height. So this is your height to which it has risen. The area of this triangle means how large the height of that point to which it rises. But if they ask you to calculate the height of the building, height of the building is simply, height of the building is this height minus this height through which it falls. So if this is the height, let me write this as capital H and this as small h. So this is capital H, the height to which it rises, the maximum point, the position where it comes to rest. Then it starts falling, but it falls only through a height labeled by a small h. The height of the building is the difference of these two. So capital H minus small h gives me the height of the building. Height of the building. So there are several questions in the exam in which they ask you to do this kind of calculation. They want us to know the height of that surface where the object ultimately lands, and by calculating the areas of these two triangles, by taking the difference, we can calculate the height of this surface. And in similar way, there are other ways they ask these questions. For example, one way of asking a question is, what if you initially are here at the top of a cliff. You have thrown an object up through a small height, but it falls far below, and this is a surface of water in which the object ultimately drops. So this rises to this height. Let me label this as small h now. This is capital H now, the height through which it falls, the distance through which it falls. Obviously, the shape of this graph will be different now, and let's make that graph now. Now, instead of a large triangle on this side and small on this side, we have small triangle here and large one on this side. So this will be the kind of graph now that we have. So this is the small height through which it rises. In this case, this is the maximum height to which it goes. And then this is the point, this is the time at which it was at the maximum height. But it starts falling from this, and all this area shows the distance through which it falls freely. So this is denoted by capital H. So what is the height of the cliff now? What is the height of the cliff from which you have thrown the object? Obviously, it is this minus this now. So the total height through which the object has fallen minus the height to which it rose when it was thrown upward. You take the difference again, but now the difference is from this triangle to this, and you get the height of this cliff now from which you have thrown the object. So this is, sometimes the object is above the surface of water, and let me discuss that one as well. An object is dropped an object that is dropped from a small height above the surface of water, above the surface of water. Because the object is dropped from a small height, so initially it is expected to have a straight line graph because it will fall with the constant acceleration. But this is the point where it makes an impact with the surface of water now. So with the surface of water, it quickly slows down, but obviously it will not rebound. It goes into water, slowing down quickly, and then more or less, this shows deceleration. In a very short time, it acquires a smaller velocity, and then this becomes constant afterwards, more or less constant velocity with which the object moves. So this is the kind of graph which shows the object makes an impact with the surface of water. It quickly slows down, decelerates. It is just like opening a parachute. You have seen this kind of graph for opening a parachute in overlevel classes. This is the time for which the climber falls, and suddenly it opens the parachute, it quickly decelerates, and then the velocity becomes constant, the terminal velocity with which it subsequently falls. This is the kind of graph for this situation. We have this graph in the exam in one of the recent paper 1 questions. So this is all for today. We'll continue discussing graphs in the class tomorrow, inshallah. Thank you for today.